So hello at the last session of problem analysis. So yesterday contest was text algorithms, and we will be talking about that. So as usual, we start with the easier problems. So the easiest one was problem G, palindromic finder. Okay, so in this problem you have a word, and you have to test whether there's a palindrome of length at least 3. So if we can have some kind of word. All right, and a palindrome is the subword. Like a palindrome is a word which if you read it from left to right and from right to left, it's the same. So we would like to find some palindromic fragments in this word. So for instance, this long fragment is a palindrome, because if you read it from left to right and from right to left, it's the same. But we also can have other different palindromes, like this one or this one. Okay, and usually if we want to find the palindromes in the word, we would like to find the longest ones. So for instance, this will be the longest. This will be the longest. We cannot extend it because here we have A, here we have C. And there's the palindromes have this nice structure that if a word is a palindrome, so the shorter word, if we ignore the first and last letter, it's also a palindrome, and so on. All right. So we can use it to produce to think about an algorithm which for every position which is in the middle of the palindrome, it will return as the longest, the longest radius of the palindrome. So the longest palindrome who's centered in this letter. So these are odd palindromes because they have odd length, and we can also do similar thing for the even palindromes. So the palindromes which are centered between two letters. We know an algorithm for this. There's a Manacher algorithm which calculates all the radiuses of palindromes in linear time. So we can say, okay, so let's use this algorithm, and then we will find whether we have some palindrome with length at least 3. But this is actually a very easy task, because we don't need to use any fancy algorithm. Because we can just see the structure of the palindromes. So if we have some long palindrome, then we also have shorter palindromes of the same parity and shorter lengths. So basically, if we know that we have some odd palindrome of length at least 3, we know that actually we have also a palindrome of length exactly 3. All right? And the same with even palindromes. If we would like to find out some even palindrome of length at least 3, that means that this palindrome must be of length at least 4. So basically, we need to find a palindrome of length exactly 4. So for instance, here we do not have this palindrome. But we have an odd palindrome of length exactly 3. So we can say yes in this problem. So what we have to do, we need to find palindromes of length 3 and 4. So finding a palindrome of length 3 is we're just iterating over the subwords of length 3, and we just need for every subword x, y, for every subword A1, A2, A3. We just need to find out whether these two letters are the same. And for even palindromes, we need to find whether these two letters are the same and these two letters are the same. So overall, the time complexity is also linear, but the algorithm is much more, much simpler. All right. So that was the first one. All right. The next problem, I think we'll go to problem B, DNA. Yeah. So in this problem, we had two words which consist over alphabet of size 4. So maybe I will just write down the example. All right, and the story was that this is a DNA string of the two species, and they will need to they will cross with each other to provide a DNA of an offspring. And there are some rules. How do you find this DNA of an offspring? So basically, these strings are of even length. And you need to for every position in the offspring string, you need to either take a letter from the top string or a letter from the bottom string. But you have to take exactly half letters from the top and half letters from the bottom. So you can. So there was like. Okay, we'll go to the detail soon. And one additional requirement is that the resulting string here must be as lexicographically first among all possible strings you can get. All right. So what can you do? So for instance, if we have let's say we have for the very easy example, we can have these two strings, and then we can try to find a lexicographically first, so we can use some greedy approach. So we say, okay, so A is less than C, so we say, okay, so here we will have A, and we will use the letter from the top string. A is still less than C in the second position, so we also use A and the letter from the top string. But now we have used all the letters from the top string we can use, because we can take at most n over 2 letters. So now we are forced to actually use the letters from the bottom string. Okay. So we could use this kind of greedy approach, but we will encounter one problem. So if we try to use this greedy approach here, so first A is also smaller than C, so we will use A here. But now we have this situation when both letters are the same. So we know that we must put T as the second letter of the solution, because we have no choice. But actually, we don't know from which of the parents it will be optimal to take this T. Okay, because if we take wrong parent, so for instance, if our example will be something like this. All right. So we know that in the answer we need to have T, but if we take T from the first one, then we won't able to. Then we cannot take A, we will be forced to take C because we already took half of the elements from the first string. And this is not an optimal solution. Yes, the better solution will be to take T from the second and A from the first. So the problem is that we don't know what to do here. So we would probably we need to find some like optimal solution here and then see whether which of the strings we can take. But we can do another approach, and basically we can, since we know that this T here is for sure, we can just go further and say that okay, we decide which T from which string we take this T at the end of the algorithm. So basically, so far we know that we for sure take A in the first string, and that's it. And we will take T from some string, but we don't know yet from which one. Okay? So for every element which is the same, we just put this element and we continue. So now we have G and T. So G will be smaller. So still we need to take from the first row. Then C is smaller, so we take from the second row. A is smaller, we take here. A is smaller, we take here. So now we cannot. So basically we are at the end, and now we see that since we taken everything from the first string, we know that this T must be taken from the second one. Okay. So basically, in the algorithm, we need to we'll do a greedy approach, and we will keep track of how many elements we have used from the top row and how many elements we have used from the bottom row, ignoring the elements which were the same. And if we end up in the position that we have used everything from the top row, then we need to like continue using only elements from the bottom row and vice versa. And at the end, we can fill the elements which are the same with the elements of this row in which we have still left. So overall, this was like a linear algorithm, but because of this equal elements, it was a little bit tricky. Most of the like incorrect submissions were due to a time limit, because in this problem time limit was pretty low. So once again, the input output, if you're like in this problem, input size and output size are both linear, and your algorithm is supposed to be also linear. So actually, most of the work your algorithm will do is for inputting and outputting data. So you don't want to this input and output to be slow. So rather than using like C and C out, I suggest to use printf and scanf. And also, if you're using printf and scanf, don't use it like character by character, because it still be slow. Because then instead of like using C and C out, you have to use like 1,000,000 times of printf person C. So actually, this is quite if you use this operation like 1,000,000 times, it will be slow. So don't use that. Use just like prepare a string in an array and then use %s to print out the whole string in one operation. All right. Questions? All right, so we can move to yet another DNA problem, so problem C. Yeah, usually like for this text, for this problem, so in text algorithms, usually the stories involve around like this DNA sequences, because like it's also like one of the most important applications of the text algorithm is computational biology. So also it's not very strange that problem A was called computational biology. All right, C. So like DNA 2. So now we are giving some DNA string. So let's say something like this, and we would like to create a string with the same length, but in such a way that the longest common subsequence of these two strings will be as short as possible. So maybe let's produce some random answer, and then we can think what is the longest common subsequence here. So for instance, if I take A, C, T, A, here I can also take A, C, T, A. Yeah, actually I can then even longer one. I can take this T. So here I produced a random answer which has like the longest common subsequence of these two is 5. Okay, I cannot do any longer because this G is here and this is C. All right. Okay, so this is this word has 7 was of length 7, and we have like LCS of length 5. So this is quite big. Maybe we can think about some shorter subsequences, and this is like if you look at that the first time, it may be maybe we need to do some complicated like dynamic programming, because like LCS calculated by dynamic programming. So maybe if we want to like minimize the length, maybe we also need to find something like this. Especially that the length of the word was up to 10,000. So it's like it looks like some quadratic algorithm should be here. But we can think about some easier cases. So let's so one thing, one way of like simplifying this, we can think about what if your word consists only of one letter. So what if your word is like A. So what can you do now? Yeah, I can just use any other letter. So basically, I can take any word which does not contain A, and this will produce the word with LCS equal to 0. All right. So the thing is that if we have like more complicated word, I can also in the more complicated word I can also take some kind of letter. So let's say that I take all letters A, and I can think about what will be, like if I put my answer, how the LCS will depend on the letters A. So basically, if in my answer I have 2 letters A or more, I know that the LCS will be at least 2, because like if I see only letters A, then their order doesn't matter. So if I have at least 2 letters in my solution, then LCS will be also of this length. So I can try to think, all right, so if I know that, so either I cannot put any A, or my number of A's must be small, but if number of A's in my solution is small, then some other letter must appear more frequently. So the one idea could be like this. So I could take the C, G, and T because they were not appearing here in the string. So maybe if I will write this once again. So maybe I can take a letter which appears very infrequently in my word. So and then I will just construct a word which consists only of of this letter. All right? So because I have all letters G, I know that the LCS here in this example, so LCS will be the number of letters G in the input. Okay? But since the letter G was like the letter which appears like least frequently, then I know, for instance, that this will be not bigger than n over 4. Okay? And this is something promising. And actually, we can prove that this will be the optimal solution. So how can we prove it? Well, so let's suppose that like the G is the letter which appears like least frequently. So we know that the number of appearances of G is smaller to numbers of A, of C, and of D. All right? And let's construct like any. So let's say that we have like any solution. So then we know that that in our solution here, like in any string, at least one letter must appear. So at least one letter will have this property that the number of this letter is at least n4. Okay? So the number of appearances of this letter, since G is the smallest one, will be actually greater than this. All right? And here, all letters have this property that they are greater than this. So actually, also this letter L, so this is like number of letters L which appear in our second string, and this is number of G's which appear in the first string, and this will be okay, yeah, and so the equality is in the other side. All right, but so the numbers of letters which appear, numbers of letters L which appears in the first string is also greater or equal than numbers of G's. Yeah, because we have this one. So it means that numbers, this number, so numbers of letter which appears here and numbers of L's which appears here are at least G. So that means that we cannot construct LCS with the smaller length. So actually taking the least frequent letter and producing a word which consists only of least frequent letter will result in a correct algorithm. Yeah, and like the time complexity is linear here. So we didn't have to use any fancy thing. So one question is why the n was up to 10,000 and not, for instance, 1 million? Sorry?
To make us think that ADP might work.
I didn't.
So that we could try ADP.
Okay, so the answer is that you can try DP. Well, it was. It wasn't the main reason. So it was like because it's 10,000, you can try DP, but it wasn't like the main reason, right? Yes, because we have to provide a checker. Because if you like, because you don't necessarily have to like follow the model solution here. So if you write any word, we have to check that the longest common sequence of the input word and your solution is optimal, and we cannot do it faster than n squared. So in order that the checker like works fast, the output couldn't be like 1 million. All right. So yeah. So now we move to problem D. So this is problem about Balthazar, who makes some necklaces, and he has a very long string. and he would like to partition this string into pieces. All right, so the idea is that we have a string consists of numbers, and so yeah, maybe I write the first 1, 2, 3. Okay, maybe something like this. And we would like to partition it into pieces of the equal length. So now first we choose the length, and then we would like to have as many different pieces as possible, provided that we can also rotate a piece. So for instance, if we have k equals to 1, then we will just partition this string into pieces of length 1. And what kind of pieces can we get? Well, we can get piece 1, we can get 2, and we can get 3. So nothing interesting here, all right? But if we take longer pieces, then things will start getting interesting. Yeah. So first we will get 1, 1. Okay, because this is the first one. Then we will get 1, 2, 2, 2. We'll get also 3, 3, 3, 1, 2, 3, 3, 1, and so on. And if, for instance, if this 3 and 1 was, if you have something like this, then these two will be the same. So actually, we will get 1, 3. And 3, 1, because we can rotate them, so 3, 1 is actually the same. So for 2, we will get we'll get 2, 1, 1, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, and that's all. All right? And we are doing this for every possible k. And we are interested in numbers k, which results in the most, the biggest number of different parts. So here, the number of parts is 3. Here, the number of different parts is 6. Okay? So we would like to know the number of parts. So let's suppose that we can compare these parts in constant time. Okay, this is like for the very short parts, of course we can do it. If the parts are longer, then it's not necessarily obvious how to do it, but let's suppose that we have that. And let's see how we can solve the rest of part of the problem, provided that we can compare the strings. So the idea is that we can actually test all the possibilities of k, and calculate the number of parts for every different k. So basically we're just writing a loop for k equals to 1 from 1 to n, and then we need to partition string into n over k pieces. Okay, and then we need to if we can compare these pieces like in constant time, we can just sort them. We can just sort them and remove duplicates. Okay. So we can sort them and calculate the number of different pieces. Okay. So suppose that we can, like, when sorting, we can use like the constant time comparisons. So how long this code will take? Well, it looks like it's somehow quadratic, because here we have this loop over k, and then if we want to, and then we will have like this loop over n, because we need to partition the whole string. But the thing is that for bigger number of for big values of k, these elements will get longer. So actually, we will have smaller number of these elements. So we need to be more careful about the complexity. So basically, the complexity will be we need to. So in the first round, we will have n to partition string into n pieces. For k equals 1, we'll get n. Then n over 2, then n over 3, then n over 4, and so on. And also we need to sort them. So actually, for sorting, we will need n log n algorithm. So basically, all of these things here are like n log n, n log n over 2, n log n over 3, and so on. But you can like just put log n here. It will be also not good. So this means that this will be n log n times this number. So this is like a harmonic sequence. And it can be proved that this is actually log n. This is no bigger than log n. So overall, the time complexity will be n log square n. Okay, so pretty nice. But we need to find how to compare the strings. And this is like one of the most important topic for text algorithms. And we will show two different ways how to do it. One is hashing. So this will be like the randomized solution, which is often pretty fast and has nice applications, but there's a small probability of error. And the second way will be that's a data structure called, we call the dictionary of base subwords, but it has different names. It's used in the Karp-Millen-Rosenberg algorithm for the pattern matching. And it's also named, I think it's in some senses, a sparse table. So it will be a structure which will be needs a little more time to construct, and it will be less flexible, but it will give us 100% sure answers when comparing the substrings. Okay, so first one, hashing. So for hashing, we'll just the idea is to present this like the parts of the string as the number in a very big base, and then to take this number modulo some big prime number. So basically, we have something like this. If our string is like A0, A1, A2, A3, up to some kind of AN, we can obtain the hash of the string. So the hash will be, so let's say the hash of string A will be A0 times plus A1 times some, let's say, A plus A2 times A to the power of 2 plus A3 and plus AN to the power of n, and everything will be we'll take modulo some prime number p. All right. So if we want to compare two substrings, we would calculate these numbers for the substrings, and then we just compare the numbers. So there will be some because the number of substring of length L is like exponential. There's exponentially many some such strings, and we have only like p. Usually we will use some like prime number like 10 to the power of 9 plus 7, something like this. So there's more substring than this kind of numbers. So we will definitely have some collision if we take a lot of these strings. But if we are only like comparing two random strings, then the probability of collision is small, because if the like lengths of these strings are n, then probability is like n over p. So if p is big, then the probability is very, very small. If you want to like reduce the probability even more, you can do hashing 2 times with 2 different prime numbers, and basically you can get this probability as low as you want. And if this probability is like very low, it starts to be even lower than probability that your computer will explode during like proceeding your program. So actually, like the collision of the hashing is not the worst thing you can imagine. All right, so this is it. So how can we fast calculate the hashes for some substrings? So suppose that we have a string, and we have like this letter AI, the beginning, and our string ends at say at a j minus 1. So we'd like to calculate the hash for this part. So one way to do this, we can do a prefix sums or suffix sums for the hashes, and then we could just calculate the hash for the one prefix and subtract the hash for the smaller prefix. Or if you calculate the hashes for the suffixes, we can calculate the hash for the suffix and subtract the small one. So yes, so we can. So suppose that we calculate the hashes for the suffixes. So let's say that hash of n is equal to 0, and then we can write down a loop which says that hash of the, so this will be hashes for suffixes. And hash for suffix I. So in order to calculate the hash for some suffix I, we take the hash for suffix I plus 1. We multiply this hash by a. So basically, that means that in this equation, every letter will be multiplied by another a, so we'll like shift this hash, and we can then take a letter at the position I. We just add it, and of course everything is done modulo p. All right. So these are hashes for every suffix of this string, and if we have this kind of hashes, we can calculate hash for subword from I to j minus 1, and this is just a hash of the whole suffix starting with I. So we are calculating this hash, and we need to subtract the hash starting from letter I. So we need to subtract hash from letter j, but this hash here was aj plus 1 times a, and here if we're starting calculating hash from I, here we have ai plus 1 times a, and if we go here we will have aj times a to the power like j minus I. All right. So basically, we need to multiply this part by a to the power j minus I in order this thing works. All right. So what will be the time complexity here? So this is like the pre-processing, and it takes time, linear time over the length of the string, and this is a query, and this takes it takes constant time, provided that we can calculate this power. We can calculate it on the fly using fast exponentiation, but then it will take logarithmic time. So then the query will take logarithmic time. So it's not constant anymore. But we can also see that the number of these powers, we need a linear number of these powers. So we can also pre-compute them all, and then the query will have query in constant time. So how can we solve our problem? Well, we have our string, and we can build this hash structure over the string, and then if we need to compare two substrings, we just compare their hashes. Okay. But here we have one additional piece of to this program, because we said that these parts can be rotated. So actually, it's not comparing their hashes is not enough, because when comparing hashes, we are actually comparing this strings, and we are assuming that they will be like that we cannot rotate them. So in order to compare 3,1 and 1,3 as the same, we need to do something more clever. So actually, what we can do is we would like to compare. So if we have like hash for 3,1, we would like to have also for this one hash of 3,1. So what we can do, we can reverse this substring and compare the hash of this reverse. All right. So maybe if you have like any two substrings, we need to compare the hash of one hash of substring S. We need to compare it to hash of substring T, and also we need to compare it to hash of substring T reversed. So in the reversed word. All right. And how to compare the hashes of reversed word? Well, we can just reverse the whole sequence, and then do the same idea as here. Okay, so we will have the structure which allows us to calculate the hashes for all the reversed substrings. All right, but then we need to take care. So if this is, so let's say that we would like to compare these two. So if we have, so this is like string A, and this is A reversed. So basically it's like 2, 3, 1, 3, 2, 1, 3, 3, 3, 2, 2, 2, 1, 1, 1. And we have hashes for this part. So in order to compare these two, so this is S, this is T, we need also to compare T hash for S with T reversed. But T reversed is over here. So we also need to take care of the proper indexing. Yes, so not only we revert our string, but also we need to, if we have like position I here, so here we will have like position n minus length minus I plus minus 1, something like this. And yeah, and getting like this plus number one is sometimes tricky, so we need to pay attention here. All right. So what will be the time complexity of our algorithm here? We show that it will be n log square n if we can compare the substring in constant time, but thanks to hashing we can do this. So we only need to add a complexity of calculating hashes, but this is just a pre-computation which takes linear time. So overall the algorithm will be n log square. All right? Questions? Okay, so can we speed it up? So first question, can we improve the time complexity? And second question, can we remove the randomization from the solution? So we would like some different thing than hashes. And the answer yes for both of these questions is yes. So we will now use another approach for dealing with hashing, for dealing with comparing substrings. I'm not sure which part I can. Yeah, I think I will leave hashing for now. Yeah, let's say that we already know the algorithm, so I will remove this part. So this will be the dictionary of Bayes subwords. So idea is that we would like to, as the same as with hashing, we would like to, for every substring, we need to find some small number, which will be an identifier of the substring, in such a way that if two substrings are the same, they have the same number. All right? And this is what hashing did, but we would like it to be even more strongly. So if two subwords are different, then they will have different identifiers. And this is what hashing cannot guarantee. Sometimes we can have collision, but we would like to have this guarantee. So the idea is somewhat similar to the base segments in the segment tree. So we will use here the powers of 2. So suppose that we have here our string. So yeah, let's draw it once more. All right. So we will provide a number for every substring which size is equal to power of 2. So yeah, so for instance, this one, this one, also this one. So so if we recall the segment trees, in segment trees you have like linear number of this kind of base intervals, because like these intervals were in such a way that they like intervals of the same, which have the same length, does not intersect with each other. But here we will use every possible interval of length, I say like 4. So basically, on every level, we will have n intervals, around a linear number of intervals. So we will have like linear number of intervals, or I would say subwords of size 2 to the power of k for every possible k. So that means that we will have n log n subwords. All right? Okay. And first we would like to, for these subwords of size power of 2, we'd like to give them these identifiers which allow them, which will allow us to compare them. So first size, so let's first take k equals to 0. So what can we do here? Well, we can just give the identifiers based on the just letters. Yes, because every string is just one letter, so we can give these identifiers. And actually, we would like these identifiers to be small, so we just sort all the letters, and we just renumber them as consecutive integers. So for instance, here we will have 0, 0, 0, 1, 1, 1, 2, 2, 2, and 0, 1. All right? So this is like the easy case. So we have to like only renumerate them. And now it's a harder case. So basically, if we have like a range of size 2k, we would like to give the identifier based on ranges of smaller size. So here we have two ranges of smaller size. So basically, we know that the ranges of smaller size have unique identifiers. So we'll have some identifier A and identifier B. And we know that for the smaller for smaller ranges, if two ranges have the same identifier, then they are the same. So how can we identify the bigger range? Well, we can just concatenate these identifiers, or in other words, we take a pair of smaller identifiers. All right? So then if we compare two words of the length 2k, so if this word has identifier like AB, this one has identifier CD. So if they are the same, if and only if A is equal to C and B is equal to D. Yes? But then it means, since this C and this D comes from these parts, that the left A must be equal to C, so the left part is equal to the left part, and B is equal to D, so the right part is equal to right part. So, like, these pairs are good identifiers, if A, B, and C and D are good identifiers. All right, but if we continue like constructing these pairs, then these identifiers would get quickly complicated. So what can we do if we have this kind of pairs? So we can take them all, sort them, and once again give them small numbers. So for k equals 1 here, so we will have like identifier, here we will have 0, 0, because we take 0 and 0. For this one also 0, 0. For this one 0, 1. For this one we will have 1, 1. For this one also 1, 1, 1, 2, and so on. Yeah, I think 2, 2. I think I will just make this example a little shorter. All right? So these are the pairs from the substrings of length 2. So for instance, this one comes from the fact that here we have 1 and here we have 1. All right? And now we can sort all of these pairs once again, and we can give them small numbers. So for instance, if we sort them all, yeah, let's make this example more interesting. So let's replace here with the 2, because now if I sort it, it will be like trivial. So let's say that here we have 0, 1, and 1, 0. Okay? I just made the example more interesting. And now I need to sort all of these pairs. And after sorting, I will just give them numbers. So the lowest pair is pair 0, 1. So I put 0 for this pair. The next one lexicographically is 1, 0. So I put 1. The next one is 1, 1. So I put 2. The next one is 1, 2. I put 3. And the last one is 2, 2. So I can say it's 4. All right? So now on this level, I have identifiers, small identifiers for our subwords. And since there will be like at most n subwords on each level, so actually these identifiers will be numbers which are less than n. So it's quite nice. So we can do one more level. So let's say that we are doing it for k equals 2. So what will be the pair for the first one? So the first one will have 0, 0. Okay. The next one, 1, 2. The next one, 0, 2. 0, 2. The next one will be 2, 3. 2, 3. And the next one will be 2, 4. Yes. And this is the last one. Okay. So once again, we can renumber them. And actually, here we will see that all of the substrings of length 4 are different, because we will get like 0, 1, 2, 3, and 4. Okay? All right. So thanks to this structure, we can compare any two subwords which have the length of power of 2. Okay? So we are just we need to find the correct row and correct indices in this array. And since this array is of size n log n, the computation will also take time. Well, okay. So what is the time complexity of calculating this? Okay. Uh-huh.
Each one we can like calculate the pairs in linear time.
Uh-huh.
We can start doing some kind of right start kind of thing. So
All right. So we have here log n levels. So we have log n levels, and yeah, actually it's exactly log n. And on each level, we need to create the pairs, which can be done in linear time, but also we need to sort these pairs. So if we do like normal sorting, we will get n log n for each level, and then the algorithm will be n log squared. But we can use our standard trick of sorting, because we said that these numbers here are small numbers. They're smaller than n. So we can use counting sort to count the pairs. So actually, we need to like sort them according to the second coordinate, and then we need to stable sort them according to the first coordinate. All right? So if we, so either we do just normal sort and then we'll get n log squared, or we do like counting sort twice, and then we can go to the linear complexity for one phase, and the overall will be n log n. Okay, so preprocessing is n log n, but how can this help us? Since we showed that we can calculate the identifier for each substring which has length of 2k, but we'd like identifiers for every possible substring, so not necessarily of length 2k. But so how can we do this? So if we have some substring of length L, we'll just cover this substring with two subwords of length equal to power of 2. So we take the biggest power of 2, which is no bigger than L. So we take some k that 2 to the power of k is no bigger than L, and then we know, then we can take some substring here of length 2 to the power k and some substring here. All right. So we take one substring of length power of 2 which starts at the beginning of our subword, and the other one which ends at the end of our subword. So basically they will both like cover our word. All right. So we know that these have some identifiers, like this can have like identifier A, this will have identifier B. So what will be the good identifier for our word? We can take AB. All right. So, well, the thing is that we would like to compare this L with some other subword of length L, and if in this other subword we also take this kind of identifier, so basically we will do the same as here, but this smaller ranges can overlap. But this really doesn't matter, because what we want is that both of these ranges actually covers the whole sequence. So the same argument which we showed here, that these identifiers are correct, we can also apply it here. So if we want to compare two subwords, we need to find the largest power of 2, which is smaller than their length, and we take two identifiers from our table for every word, and then we just compare two pairs. All right. So comparison will be in constant time after we did the preprocessing, and this will be like 100% sure solution. So if we see that the identifiers are the same, we are sure that the words are the same. What will be the time complexity of our solution to problem beats if we use this approach? Well, first, this approach doesn't use randomization, so we answered one of our questions. But second, remember that our algorithm for beats was n log squared because we did sorting inside. But now, and we need to do n log n sorting for hashes because hashes are big numbers. But these identifiers are small numbers, so we can once again use counting sort inside our bets algorithm, and then we will get n log n solution. N log n solution for our algorithm plus n log n preprocessing to get this table. All right? Questions?
That's like a similar idea to suffix arrays, right?
Well, suffix arrays gives you the information about the suffixes. Here, like, you get the information about all infixes which are of length power of 2. So
Do you have like an implementation like kind of algorithm and power to
all right. In this sense, yeah. In this sense, it's similar. Okay, so since we have like 10 minutes to the break, maybe we can see some applications of these two structures, and one additional thing to this algorithm. Since we still need to compute also we still need to compute the identifiers for reverse substrings. All right. So how can we do this? Well, if we did the hashing thing, we could provide like the hashing for A and additional hash table for A to the power of R, and then we can just compare. Since we use the same algorithm for hashing, we can just compare them. But the problem with this dictionary is that we actually need to know all the possible subwords of length to the power of k in advance, because we need to sort them all and give them identifiers. So actually, we cannot use different data structures for A and data structure for A reversed, because then we cannot compare identifiers from these two structures. So what can we do?
We are making the assign the IDs. We can assign the same ID for the element that has the reverse element.
All right.
I'm not sure if I misunderstood.
Yeah, okay, but if we assigned it here, then we actually will, like, it's not clear that we will correctly assign these values, because then like reversing these two values will be like reversing these two parts, and yeah, I'm not sure if it's gonna work. So the one idea which would work is if we could like assign the identifiers both for this strings or for this string, like in one go, in one structure, then if we are comparing two strings, we can just compare the identifier for L and identifier for the next string and its reversal. So we will do the same as hashing. But the thing is, like, we need to be able to, when doing this process, we need to know the strings both from A and from AR.
We can concatenate like strings and put some special.
Yeah. So the idea is that we can concatenate these two in one string and then construct the stable for one string. So we can construct like A. We don't even need to put any like hash between them. We can just take A and AR. All right? So every substring which appears here and here, it will appear here. So we are fine. All right? So we can just calculate one dictionary for the word A concatenated with A reversed. And actually with hashing, we could also do this. We can just use hashing for this whole string. All right. So what about other applications? So we showed that that we can compare whether two words are the same. Can we compare if two words are, like, which word is smaller, lexicographically smaller than the other one? All right, so we have like some S and T. We know that if we want to compare S and T, it's the same as like comparing their hashes or comparing their identifiers. So let's say that this is like the identifier of L. All right? But what about like S being smaller than T, lexicographically?
Compare by first item of the tuple and the rank types of the second type. Like A, B, and C, D, where A with C.
Mm-hmm.
And if A is less, so this is smaller. And if they are the same, then I compare B and C.
All right, so this will be the solution with identifiers, yes? Yeah, so basically for identifiers we can do this. So first, if we have like this identifier which is a pair, first we need, since we are comparing lexicographically, we need to first compare whether this part is smaller or yeah, so if we have like L and L2, so first we compare A with A2, and if some of this identifier is smaller, then we know which word is smaller, and if they are equal, we just have to compare B with B2. All right, so we compare these pairs lexicographically, but we need to, in order to do that, we need to know that if we have two identifiers which are powers of 2, then the order of the identifiers is the order of the subwords. So we need to know that if one identifier is smaller than the second identifier, that means that this subword is lexicographically smaller than the other subword. And the question is this true or not?
It's true, because when you're constructing the dictionary, on the first level, on k equals 0, they are sorted.
Yes.
And every time you merge one level to create the next one, you sort it again, so they are already sorted.
Yeah. Yeah. So the answer is yes, we have this, because on the first level you have letters, and of course it depends on the sorting order. So if you like assign these numbers like in whatever manner you choose, so then you have this guarantee. But if you assign these numbers in the order of the letters, so you basically sort the letters lexicographically and then you assign the numbers one by one, then you know that you have this property for k equals 0. And if you for greater numbers of k, if you sort the pairs lexicographically, then you will also have this property, because like comparing these two words, first you have to compare A with C and then B with D. So basically it's a lexicographically comparison. So for identifiers you can do this. So if you construct identifiers such like this, then you can compare in constant time whether some word is lexicographically smaller than some other word. And it's really nice. Can you do this with hashing?
With binary search.
All right. So like comparing only hash values comparing only hash values is not possible to get this, because like these classes are really random numbers. So we cannot do this in constant time, but we can use the binary search to compare this in logarithmic time. So basically, if you have like a word one word and the second word. And if you compare their hashes, and if they're the same, so you know that these words are like with big probability they're equal. But if the hashes are different, well, you can binary search for the first place in which these two words are different. So basically, you will binary search for a letter for the place in such a way that this hash and this hash is the same. So let's say this is like position I. So hash of s from 0 to I minus 1 is equal to hash of t from 0 to I minus 1. All right? So this is the longest hash which matches. And then you know that the letter after this hash is different. And then you can just compare these two letters. All right? And the letter which is, the word in which the letter is smaller, it's smaller lexicographically. And since you are doing binary search, you can do this in log n. And also, the same idea will allow us to calculate the longest common prefix of two words. So basically, this number I is the longest common prefix for subword S and subword T. Okay? So this can be done in logarithmic time. With hashes, can we do with identifiers to calculate the longest common prefix?
In the logarithmic time, like comparing if we're citing in both tuples and they are like the same plus proceeds smaller power.
Yeah, we can do like we can try to think about like clever algorithm, but it still will be in logarithmic time, and actually we can use like the same approach as here. All right. So rather than comparing the hashes, we'll just use the binary search and directly compare identifiers to calculate LCP. So for hashes, so both for hashes and for identifiers, calculating LCP will take a logarithmic time. But of course, for identifiers, it will be not randomized solution. So it will be sure that we have this. All right. So break. All right. Okay. So the next task will be task E, mutations. All right. So in this task, we have two sequences, and we will be comparing subwords of these sequences. So maybe we can use some knowledge from what which we have here, like hashes or some kind of identifiers. So the problem is that we have some, let's say, like one sequence and the other sequence. And we are asking whether the queries we will be answering is, suppose that we have like this subsequence and this subsequence. So suppose that they are not the same. So then we are asking whether they like similar. And there's this notion of similarity, which allows us to make one mutation in a string to get another string. So what is the mutation? Mutation means that we can change one letter to or one number to some other number. But if we change this, we change all the occurrences of this number in a substring. So for instance, here we can change all occurrences of 2 to 6. All right, and then these two substrings will be the same. All right, and we have a bunch of queries asking us whether we can do this or not. Okay, so we can try. So first we can like compare their hashes or identifiers and test whether these words are the same. But if they are not the same, that we know that we need to at least do one mutation. So first thing we can ask. So what will be the mutation we have to do? Yeah. So here, so in this example, we know that we have to change 2 to 6 or 6 to 2. Well, but in general example, so maybe the substring will be like 1 1 3 2 4 2 1, and the second will be 1 1 3 3 4 3 1. Okay. So in this case, what should be the mutation? Yeah, so we have to change 2 to 3. Okay, so we need to find this element, but we can use the notion of LCP we have before. So actually, we can find the first element which is different in those two strings. So if we go here, we will find 2. If we go here, we'll find 3. All right. So if the elements are different, so we know we have to use the mutation which transforms this letter into the other letter. Right. So we know what mutations we need to find, and so we can calculate this LCP in logarithmic time. All right. So in log n, we can calculate what kind of mutation we need to do. All right. So then it's not we are not finished, because then we have to actually perform this mutation and see whether we get the same words. All right, because for instance here, if we perform the mutation, we actually will get the same words, but maybe if this word here was like 3, then even if we perform the mutation, we'll get different words. All right, so what to do? Well, we can try to replace, like do this by definition. So replace every occurrence of 2 with 3. But then, like this, if there are like multiple occurrences, then all of it will be too slow. All right, so the idea is to actually use hashing for this problem, and we would like to remove this 2's or remove 3's. So basically, we can think of it like if this mutation is good, so actually we can, if we remove the element 2 in this word, we'll get like 1 1 3, let's say 0 4 0 1, and in this word we will get okay, if we remove all of the 3's, then it's all right, so it's not okay. So maybe so all right, so we would like to remove element 2 in this word, and then instead of these 2's which we removed, we would like to put additional 3's here. All right, so that means that like this word here can be composed like you can do this in either direction, So basically, we have like here 3 empty places. All right. We have here like empty places, and in these empty places we would like to put either values of 2 or values of 3. All right. So in terms of making a mutation, first we need to remove the 2's to get like empty places, and then we need to put values of 3 here. So how to remove it? Well, actually, it's quite. If you use hashing, then the hashing are like additive. So actually, you can partition your string into like different parts, and you can use the hashing to actually combine the strings together. So, all right. So maybe this. So for instance, if you have like string a0 and 1 and string a2 and a3, so you know that if you have hash value for this one, and if you have hash value for this one, all right. So how can you compute the hash value for the whole string? Well, the hash value here is a0 plus some kind of a times a1, of course modulo p, and this one is a2 plus a times a3. All right. So if you want to combine these hashes together to get a0 plus a1 plus a squared a2 plus a to the power of 3 a3, so you just have to multiply this hash by a squared and add them together. All right. So if you have 2 strings, here you have hash for s, hash for t. So hash for the concatenation of the strings is just hash for s plus hash for t, and if s is of length l, we need to multiply it by a to the power of l. Okay, so hashes are nice because they allow you to, based on the hashes of 2 words, you can concatenate them and you get the hash of the bigger word. You cannot do this with the identifiers. All right, so the hashes are more flexible, but the price you pay is randomization. All right, so we showed here that we can add the hashes to parts which are we can concatenate 2 parts, but actually we can do even more, because we can do hashes for the words which are not necessarily contiguous parts. So think about a word, for instance, like a0, a1, and we have space here, maybe space here. So this I call a3, and this I call a5. All right. And on the other hand, I have a word with empty spaces. And here I have a2, and here I have a4. Something like this, all right? So I can combine these words together. I take this one and put on top of this one, and then I will get, once again, a0, a1, a2, a3, and 4, and a5, all right? So I can combine these words together, but not necessarily I will put one word on top of the other. And actually, if I have hash for this one, and of course it needs to be told what can I put here for these empty spaces, and hash for this one, I can still just add these 2 hashes together. And what does it mean, hash for this one? Well, I just replace every empty field with 0. Right? So I will have hash for this one, it will be a0 plus a times a1 plus a to the power of 3 times a3 plus a to the power of 5 times A5 modulo P. All right? And then for this one, I have A2 to the power of A2 plus A4 to the power of A4 modulo P. All right? So I see that if I add these two hashes together, I will get the hash of the word which consists of like putting these words together. So I'm filling the blank spaces here with these letters. All right? So what can we do with this part here? So if I can, so basically I'm starting from this word, from the full word, and I would like to get a word or get a hash for the word in which every 2 is replaced by this empty field. So that means that actually I need to like decompose it into something like this. All right? So I need this kind of decomposition, and that means that I can add hashes, but I can also subtract hashes. All right? So if I know that hash from this one plus hash from this one will get a hash for this word, so in order to get hash for this word, I need to subtract from the whole hash. I need to subtract this hash which consists only elements of 2. All right? So I take this hash, subtract this hash, and I will get this one. Okay? So how can so now I need to construct a hash for something like this. So how can we do this? Well, I can just say that I have a string which consists of either of zeros or all 2s. So basically, I take all of my string. I replace every letter which is not letter 2 by 0, and I calculate normal hashes. And then I can take this hash. But the problem is that if I have then the solution works in time n, which is the length of the string, times the number of letters I have in the alphabet. Because for every letter, I have to provide the full string with hashes. And so this is not very practical if the alphabet is big. But if alphabet was like 4 letters, A, C, G, T, then this approach will be very nice. Okay, so what can we do if the alphabet is big? If the alphabet is big, that means that I have different letters in my word. So that also means that like if I select one particular letter, so probably there will be like a very big number of zeros. So so like storing all of these zeros is quite wasteful. So we would like to do something more clever. So actually we can store only elements which we are interested in. So instead of storing like the full string which can have like some number of 2s, all right, and instead like calculating hashes for everything here, we can say something like this. So I would like to calculate to have a structure which allows me to calculate, for instance, a hash for this part. All right. So actually, in this hash will only consist of 2 times some power. So it will like 2 times a to some kind of power. All right. So basically, what I would like to know is where are numbers 2 in this region. So instead of storing the whole thing, I will store only the positions where these powers of 2 are. So maybe this is like if we put the numbers of positions. Okay, so I will store that on position 4. I have 2, and I have 2 to the power a of 4. Then on position 9, I have also 2. So the full hash up to this position will be 2 times a to the 4 plus 2 times a to the 9, and that's it. All right. If I have something like if I have 2 on position 12, then I will have a third pair. So we'll have like per position 12, a to the 4 plus a to the 9 plus a to the 12. All right? And then if I want to calculate the hash value for some region, I need to binary search in my table for the first 2 and the last 2 in this subword. All right? And then I just so for instance, if the subword was something like this, then I know that I have to. So let's say that here we also have like something like value 0, so we can be so we can do subtraction. So we know that the last 2 is on position 9. So so this is this position, and the first 2 is position 4. So before that we have this guy. So we have to subtract this value, take this value and subtract this value to get a hash. All right, and because we are doing binary search here, the cost of producing this hash will be log n. All right, and so how to compute this list? Well, we will just do like normal hash computations. We'll go from the whole string, and based on which letter we are currently in, we will add new value to the list of for this letter. So for every letter we have this list, and we are just appending, and the sum of lengths of all the lists will be linear. All right. So in total, the preprocessing part for this one will be also linear. All right. Well, one simplification we can do here, because we have all these 2's, values of 2, which are all the same. So actually we can get rid of this. So we can just remove these values. And if we want to calculate this hash, we'll calculate the hash, and then we multiply the whole hash by 2. All right? But then we actually have a little more flexible solution, because we can now calculate hashes for this kind of patterns, but we can replace 2 by any value. Okay? So we can calculate the hash if here you have 2, or you can calculate hash if you have 3 or whatever else. All right? And this is actually quite useful, because what do we need here? We need to calculate, we need to subtract the hash with 2's here. So we we are starting from here. We are subtracting this value, and we get here, and then to get here we will add this value consisting of 3's, right? And this is done the same, like these positions here, these are positions, original positions of values 2, but we can use this this idea to actually put number 3 there. Yeah, of course, you can be even more clever and compress these two operations into one operation, because like subtracting 2 everywhere and adding 3 everywhere is just the same as adding 1, because you just add 3 minus 2. So we can do even in one pass. All right, so overall, calculating the hash, this hash we can done it in logarithmic time. So first, logarithmic time to find the mismatch position, and then logarithmic time to calculate this hash, which can transform us from elements 2 to elements 3. Okay? All right, questions? Okay, so if there are no questions, we can go to the problem A, computational biology. All right, so so now we have some word. Okay, this is the word from the example, and now we once again we are interested in some fragments of this word, and now we are interested in cyclic fragments. So what does it mean? That means that we can find some subword, namely like A and B, and now we are interested in such subwords that every cyclic rotation of this subword also exists as a subword in this word. So what are cyclic rotations? So we take a word, and then we just perform the operation of taking the last letter of this word and moving it to, of first letter and moving to the end of the word. So basically, we take A and move it here, and we end up with word A, B, A. Then we take A, move it to the last position, and we obtain B, A, A. And then we take B to the last position, and once again we obtain A and A, B. All right. So these are cyclic rotations of word A and B, and we can see that all of these cyclic rotations appear in our example. So yeah, so they even appear at the first. But so A and B appears here. A, B, A also appears here. B, A, A appears here, but also they appear like multiple times. So for instance, A, B, A appears also here and also here. Okay. So we would like to calculate the word, the length of the word, the longest word, which has all its cyclic rotations in this string, and also we'd like to calculate the number of these cyclic rotations, including repetitions. All right. Okay. So we are not okay. Well, we are not interested in the longest one, but we are interested in the one which has a certain length. Okay. So we have some queries, and query is like we are interested in the subwords of length m, and among these subwords we would like to take the subword which has every cyclic rotation inside, and then for this subword we would like to calculate the number of appearances. Okay. Okay, so we would like to once again we would like to somehow be able to compare the words, because if we know that we are looking for A and B, which can be like placed many times in this word, that maybe we need to compare this A and B with other positions. So we'd like to do it faster. So maybe we can use hashing. And also here we would need to be able to actually compare whether two words are cyclically equivalent. So what does it mean? So if you have this notion of producing cyclic rotations, so basically if you have like word uv, which consists of two parts, you know that you can like cyclically rotate it to obtain w u, right? Because you're just taking letters from word u, and so here is u, here is v. So you take these letters from u, put it here, takes another, put it here, takes another, put it here, another, put it here. So basically you don't have u here anymore, but you have u here. All right? And this is like also you can think about like definition that two words are cyclically equivalent if you can like partition them into two parts, and this in such a way that that part u, and you have part u and v, and you have part v and u. All right. So if you have like these partitions for two words, you can also try to find the hash of these words by using concatenations of hashes. So actually this concatenations is will be quite useful here, that we can do of concatenation. All right. So how to solve our problem? Well, we can think about this rotational fragments as so we can go from A and B using like switching one letter. So we can then go to ABA. From ABA we can go to BAA, and then we have this kind of cycle. All right. So if the word is good, so it means that every like rotational cyclic rotation appears in this word in this word. So that means that every guy here must appear somewhere over there. So we can do one thing. First, we can calculate how many of the subwords we actually have in our word. So we take A and B and now calculate how many A and B's we have. All right? So we can just iterate over all subwords of length 3 and just calculate the hash of every subword and just add 1 to this hash. So if we see A and B, we can just add 1. Then we have ABA, we put on, BAA, we put 1. Once again, AAB, we have another stone, we have AB, another one. Then we have BAC. So actually this is a new word. So we put it here, BAC. We have one, ACD. Yeah, I will change this. ACD, we also have one. CDA, we have one. DAB, we have one. ABA, another one. BAA, another one. AAB, ABA, and BA. All right. So we have a bunch of words which appeared in this sequence, and for every subword, we just calculate how many of these are here. And since we are doing a hashing here, so actually all of these will be just hash values. All right. So for every hash value, we have counted how many of them are, and now we would like to go to find actually this kind of cycle, which and for every position in the cycle, we need to ensure that we have non-empty values here. So actually we can treat it as a graph. So every hash value is just a vertex in this graph. All right, and from every vertex we have an edge to the next vertex, which is obtained by performing one rotation. All right. So now in this graph, we need to find a cycle in which every vertex on the cycle has a non-zero value, and the sum of all vertices in the cycle is as big as possible. Okay. So how to? So if we want to calculate this this graph here from, well, actually here we have only one additional edge, because from ACD we can go to CDA. Yeah, from CDA we could go to DAC, but actually here we have 0. But we can also put a vertex here. And here we also will have like cycles of length 3, but there will be no interesting cycle because some of the vertexes will have 0. All right. So the thing is, if we have a subword here, and if we want to calculate, so we have a subword, we can calculate its hash. So how to calculate the hash of the rotational cyclic rotation of this word?
Erase the first character,
Mm-hmm.
the entire hash to the left.
Mm-hmm. Yeah. So basically, if we know that this hash here, this hash comes from some from a string from point I to j. Okay. So we know that. So we know that hash in this vertex comes from this one. So if we do a rotational shift, it's just basically we take s I plus 1 to j and concatenate it with letter si. All right. So we know the hash for this one, and now we'd like to know the hash for this one. Okay, but we showed previously that we can concatenate hashes. So actually the hash for this one is the hash for si plus 1 up to the j plus hash of letter si times a to the power of length of the string. So it's like j minus I, something like this. All right. So basically, we can say, okay, so we are taking this vertex. We know that this vertex comes from some part of the word. We cyclically move one letter, and we can calculate the hash of the target vertex of this edge. Okay. So we can just construct this graph using hashing. And then if we have this graph, we just easily, we have to go through the whole graph and see which cycle is the best. All right? Questions? Mm-hmm.
So for each hash, we must calculate the hash of every cyclic rotation.
Mm-hmm. Yeah. So actually, not every, but for a subword, we are only calculating the hash of the next cyclic rotation. All right. And for this, we can calculate the hash for next cyclic rotation and so on. So actually, for every vertex, we are only calculating one edge. Okay.
Will that happen that there are two substrings that are cyclic rotations, but are far more than one cyclic?
All right.
And in that case, how we will know that they are part of the same cycle?
All right. So we just so basically our graph will consist only of cycles. So you can well, if you start traversing from this one, you can like add some identifier, like some add number of cycle. So you can just visit all the vertices. So we know that this is cycle 1, and then your visit like using DFS, BFS, or whatever. So this is also cycling 1. This is also cycle 1. This will be cycle 2, cycle 2. All right. I'm not sure if I understand the question.
Yeah,
It's
so,
like,
well, in order to get
all right,
this string to this one,
all right, okay,
more than one.
all right. But why do you need an edge between them?
Because they are, this one is a cyclic rotation from this one.
All right. But once again, why do you need an edge? Yeah, well, I constructed this graph. Well, you have an edge in this graph. In one is just like not any cyclic rotation, but a cyclic rotation which is obtained by only transforming one letter. All right. So that means that if two words are the cyclic rotations, so they will be in one cycle, but not necessarily like the consecutive ones. Okay, so if you have like a word A, B, C, D, E, so how does the cycle look like? Well, from this one you go to B, C, D, E, I, from this one to C, D, E, A, B, from this one to D, E, A, B, C, and from this one, once again, A, B, C, D, and from this one here. All right. So in the cycle, I have an edge from two words if I can just like make one letter step. All right. And since like the cyclic equivalence, it means that I can move like take some more letters. So that means that two words will be cyclically equivalent if they belong to this one cycle. All right. So if we like construct this cycle at the beginning, so then you can just ask whether and then for every cycle and every node in the cycle we'll put like this node belongs to cycle number 5, for instance. Then you can just see whether these have the same number in the cycle. So actually you can compare then whether two words are cyclically equivalent. All right? Okay, any questions? All right, so these were like the last 3 tasks were pretty much about like hashing or using the identifiers. For the mutation task, I don't know any solution which does not use hashing. So sometimes you're like we are forced to use hashing. For some problems, it's easy also to use identifiers. But for some problems, like it's easy to use hashing, but not necessarily identifiers. So actually, the problem computational biology is not very hard if you want to use hashes. But actually, this problem can also be solved using identifiers. But then the solution is, I would say, more complicated. So as a good additional problem is try to solve this using identifiers, so without hashing, right? And we can move to the last problem from the set. So problem I, Christmas chain. Okay, so in this problem we have to construct some string, but we know that the string will have n positions, and we have some constraints on the string. And the constraints are look as follows: we have two substring of the same length, and the constraint says that these two substring must be the same. Okay, so we can have like this kind of constraint. Maybe we have this kind of constraint. All right, and we would like to satisfy all of these constraints, and also and then it will be fairly easy because we can construct a word which consists of only letter A, and then every requirement will be satisfied, but we have to maximize the number of distinct letters in the word. Okay, so how we can do this? Like we can start with a very easy approach. So basically, if you think about this constraint means that this letter must be equal to this one, this letter to this one, and this letter to this one. And for the bottom constraint, you have these equalities. All right. So basically, you can think that the letters are vertices in the graph, and you have all of these blue edges, which says that these vertices must have the same letter. So what can we do? Well, if you think about connected component in this graph, it means that all the letters in the connected component must be the same. And since we are maximizing the number of letters, that means that for different components you can give different letters. So let's do that. So here we have a component like isolated vertex, so we can give him a letter A. Next we will have another component B, but then we have to traverse all of the nodes which are which can we reach from B. So this will also be B, and this is also B. All right. Then we have like letter C. So we have also C here, and we have letter D, and we have D here and D here. All right. So basically, in this graph, we have 4 connected components. So we can say that the number of letters, maximum number of letters we can have is 4. So basically, the problem asks you to calculate how many connected components in a graph you have. So it's easy, but not very fast, since we can have a lot of edges in this graph. Yeah, for each, since we can have like both number of vertices and number of these requirements are up to, I don't know, like 500,000. So then if all the requirements are long, then like the overall time complexity is n times q. So it's pretty slow. So what we can do better? One idea is like why we could speed it up. Why we can have like a hope for speeding up this algorithm? Because if you this algorithm will be slow if you have a lot of requirements and every requirement is long. All right? But then if you have a lot of long requirements, then it really means that some of these requirements will have to be redundant. So they will have to talk about the same requirements here. So for instance, if you have something like this, that this part must be equal to this part, and you have additional requirement that this one must be equal to this one. So we know that this and this also appears here. Okay. So actually, if you could get rid of in the lower requirement, you can just replace this by this part and this part. So by a smaller requirement, and still you will get the same result. All right. So the basic idea is if you have a lot of requirements which are long, they will have to somehow overlap. So we'll have like in this overlap you will get the same information. So basically maybe you can find some like a smaller subset of requirements which give you the same information. But the thing is that this overlap can be really tricky. So it's not easy to see how we can simplify things. Okay. So this is like one idea to look at this problem. The second idea is we can just try and add requirements one by one. But if we add a requirement, maybe not every blue line in this requirement will be necessary. Okay, so maybe we can just only figure out which are necessary and only do some work for this part. So for instance, if we have, let's say that we have some requirement here, and we calculated, and for the previous requirements, we already calculated some connected components. So maybe we know that the names of the connected components are like A, B, C, D, A, B. Okay? We can have something like this. And then we know that we need to connect this together, connect this, and connect this. But we can see here in this picture that actually connecting these two C's, we do not need to do anything because they're already in the same connected component. Also, this D and this D is the same connected component. So actually the first thing in which we need to do some work is this A and this D. All right? So that means that we have to union the component A and component D. All right? And once again, for this B and for this B, we do not have to do anything. And since so basically we would like to do this dynamic connected component. So we use disjoint sets for this, and we would like to do union only for the if this is necessary. Okay. Okay. So how to implement this fast? So this idea is. So I will first present this idea. This is not a model solution, but the solution which was invented by the UH++ team. But I really like this. I really like this approach, especially that we will need some hashing for this solution. So it's so I first present this one. All right. Okay, so the idea is that we would like to calculate the first place which is in which we have mismatch. All right. So basically, what we need to find LCP of these two subwords if the string on which we are finding LCP is just it consists of numbers of connected components. All right. So basically, if you think about the disjoint sets, in every disjoint set you will have a leader. Yeah, either the vertex which well, if you think about the vertices, it will in each connected component you have a number of some vertex in this component, and this will be like the leader. Or you can think about like the name of the connected component. Okay, so we have a string which consists of names of connected components, and we like to calculate the LCP, so the first mismatched position. And we can use either identifiers or we can use hashing to calculate this. So let's suppose that we have calculated the hashing, the structure for hashing for this string. Okay, so then using hashing we can find out this position in logarithmic time. All right, in logarithmic time we find the first mismatched position. Okay, what we do next? Well, if we find this position, if it says that okay, if the hashes are equal, then we don't need to do anything. If they're not equal, then we have this first position which is different, and then we will do the union. All right, so we will do some work. All right, so if we do a union, the problem is that we will have to update our connected components. Okay, so either we have to replace all values of A with D, or vice versa. So let's suppose that we replace every D. So actually we would like to do less work. So we can calculate that we have number of A's is 2 and number of D's is, if I'm not mistaken, it's 3. So it's better to change A's because there's less of them. So we will change every A to D. So this will become D, and this one will also become D. All right? Okay, so we will do some changes here. So after doing these changes, we have to update the hashes. Okay, so what will be the? So we cannot do like the hashes in the normal way, like just storing them in one, like in the single array, but we must be able to update them. So what kind of data structure can we use? Yeah, we can use segment tree. With a segment tree, we can have a data structure which allows us to calculate the hashes for substrings and also make an adjustments to our string. So basically, it means that like what property of hashings we are using here. So in the segment tree, you know that for every node like describes some some segment which is power of 2, and the child node describes smaller segments. So in order to calculate, if you have like hash of the left child and hash of the right child, to calculate the hash here, well, you need to concatenate these two hashes together. But we already did this. All right? So we know how to calculate the hashes from bottom to top in the segment tree. Okay. So we need to recalculate the hashes. So actually, it looks like a lot of work, because now we need to update all these positions, and updating every single position will take logarithmic time in our tree. Okay? So we need to calculate actually how many these updates we need to do. So we used here like a standard trick. So we said that we will change A's because there's smaller number of A's than these. So that means that if we have two connected components, so actually we will merge the smaller component into bigger component. All right. So every time we do an update on some node, we do the update in such a way that this node is from the smaller component and it's merged into the bigger component. So every time it is merged to a component which is at least twice as big as the previous one. So that means that we can do at most logarithmic number of merges for one position, for one node. All right? So for every node here, like for instance, for this guy here, the total number of changes through the whole algorithm will be at most logarithmic. So we will have at most log n changes to this position. All right? Every change requires us to recalculate the hashes in the segment tree. So that means we need logarithmic time for the segment tree. All right? So we have log n time for segment tree. So that means that the total complexity of making changes is n, because we have n elements, times log n, because every element can be changed at most log n times, time the cost of change. All right? So this will be the total cost of all the changes in the data structure. All right? Okay. So then we need to be. So then we will go back to the first thing we were doing, because now the first thing we had to do the LCP, and because now we have this segment tree, we need to be more careful about doing the LCP. Either we can just use this segment tree as a black box, and then calculating LCP actually will take us log squared time. Because like for every testing hashing we need log n time here, but if we do we can do binary search inside of the segment tree, and then we will get LCP also in logarithmic time. All right, so we can go with logarithmic time with one LCP, and after this LCP we have a change. Okay, and yeah, so we change this D, and then we apply this LCP once more. Okay, so to find the next position which is different, because we can possibly have many positions for this requirement, for which we will need some adjustment. All right, but we know that after LCP we need to do union, and union takes logarithmic time. So actually, like the time for LCP will be majorized by the time for making this union. So overall, the whole algorithm will work in n log square. All right? Okay. But so this is a really nice algorithm. The nice feature of it is that it's online. So actually, after each requirement, we know how many connected components we have. But unfortunately, it didn't pass time limit because the model solution is n log n. So it's unfortunate, but yeah, I really like this this solution. All right. So what to do with if we would like to go with n log n? So for this solution, we used hashing. So maybe we can use some ideas from the data structure with identifiers. So one like crucial idea there was that we use subwords which have length being the powers of 2. And actually here we also can use this kind of trick. So idea is the idea is like we can first convert every requirement into a requirement which has the length being the power of 2. How to do this? Well, if we have a requirement, for instance, which has length 5, okay, so we have something like this. So these must be the same. So we can transform it into 2 requirements of length 4. The first one is this, and the second one is this. Okay. And actually, this is the idea we used when calculating these identifiers, right? So now we increase the number of requirements at most by 2, at most 2 times. All right, and now every identifier is power of 2. Okay, so let's see what can happen here. So let's take the identifiers which are of the biggest power of 2 as possible, as big power of 2 as possible. So maybe we can get something like this is equal to this. The second could be like this one is equal to this one, and so on. So for every this kind of requirement, we'll say, all right, let's see only the first. Let's see only the first character in everyone, because all of them has the same length. All right. And maybe there will be like additional requirements, so we will know that maybe this one will be equal to this one, and okay. So if we have additional requirement here, so this one is equal to this one, so then we will have another edge here. All right. And we can have additional requirement that this one is equivalent to, all right, to this one. Okay, so we have also this requirement. All right, so we can so we can build a graph which talks about the first letters in every requirement. And we see that as we add more and more edges to this graph, we can find that in this graph we will have some cycles. And what does it mean that we have a cycle in the graph? Well, if we have a cycle, that means that, for instance, if I want to, I know that on this cycle every letter is the same. All right, so these 3 letters are the same. but I don't know, I don't need every edge in the cycle to know this, right? If I, for instance, if I remove this edge, I still will have the same information, all right? So basically I have a graph here, but the same information I will get using any spanning tree of this graph. Okay? So actually what I can do here, I can remove some of the requirements. Okay? And I can leave only requirements which correspond to some spanning tree in this graph. All right? Observe that I can do this only because the length of all of these requirements are the same. So basically, if you think about like the first letters, they will construct this graph. If you think about the second letters in every requirement, you will construct the very similar graph, but only shifted once, and so on. And if you have any cycle in this graph, you can remove the edges from the cycle to get rid of the requirements which are redundant. Okay? And that means that if you have some number, let's say some q number of requirements, so after this removal, you will get at most n-1 requirements. Okay? Because this will be a graph which has n vertices, and you need to construct a spanning. This not necessarily is connected, so actually it will be like spanning forest of this graph, but it will have at most n-n edges, so actually minimum from n-1 and q edges. Okay? All right, so if we have this kind of procedure, we can do as follows. We can start from the requirements of size 2 to the power of k. So we take every requirement of size 2 to the power of k, all right? And for this, we construct a graph. And from this graph, we'll take spanning tree. So we'll end up with having at most n-1 of such requirements. All right? Okay, so what can we do next? So next, if we have a requirement of size 2 to the power of k, we can split it into two requirements of, okay, so into blue requirement and red requirement. So into blue part and the red part. And these will be of size 2 to the power of k-1. All right? So we split it into requirements of size 2 to the power of k. So then, here we have 2 to the power of k-1, and we will have at most two times more. And we add here the rest of the requirements of size 2 to the k-1. So number of the rest requirements of size 2 to the k-1. All right? And once again, we construct a graph for this. So here we have like spanning tree, and we get a spanning tree, and that means that this is, once again, we can reduce it to at most n-1 requirements. Okay? So we will do in phases. In each phase, we will consider smaller and smaller requirements which has the size of power of 2. And after each phase, we do a spanning tree, so we reduce our number of requirements to n-1 at most. And then we add the next smaller power of 2, and so on and so on. So how many phases we will have? Well, we will have the number of phases will be just the biggest power of 2. So we will have logarithm n of phases. And in each phase, we need to consider the requirements of the size of this power of 2, and we need to construct this graph. All right? So to construct this graph, the graph has n vertices and it has some number of edges. So the number of edges in the graph will be n minus 1 because these are requirements which were from previous graph plus some additional requirements on this level. But overall, the overall sum of all these requirements will be q. So actually, in every phase, you do the work. For one phase, you do the work of size n plus q at most. So overall, the algorithm will work in time n plus q log n. All right? Okay. So it will be, yeah. So this one will be accepted in time. So this one is faster. It doesn't use hashing. It uses this notion of segments of power of 2. But the drawback of this algorithm is that it's not online. So we have to know all the requirements in advance to be able to sort them into different categories of different sizes, and then do a phase by phase. All right. So this will be it. So yeah. So I think we will have to stop at this moment. So once again, thank you everybody for your attention during the lectures. I hope you enjoyed it. And yeah, I hope you also enjoy the contests. And yeah, have fun.